A diagram representing alternating current and voltage as rotating vectors in which the angle between them is known as phase angle. So the magnitude value of this particular vector, that is current or voltage, is given by the length of that particular vector. Current is actually leading by 90 degrees with voltage. Hey all, I'm Hari Krishnan from the Department of Physics, Vidhyaashram PU College, the Temple of Excellence, and we were discussing about the various facts about alternating current. Today we are going to see some different quantities and different ways of representing AC current or simply alternating current. So before actually getting into how current passes through different various objects such as resistors, capacitors and inductors, we have to see one thing that is very important for this particular topic, that is phasor diagram. So what exactly is a phasor diagram? How is it different from any other diagrams you have already seen? So phasor diagram is something that converts the linear graphs into rotating vector graphs. That is, a diagram representing alternating current and voltage as rotating vectors in which the angle between them is known as phase angle. So that particular diagram is known as a rotating phasor diagram or simply a phasor diagram, in which the quantities, that is the alternating current and voltage, is represented as rotating vectors. So if there is an y-axis and an x-axis like this, so let's say this is the y-axis and this is the x-axis, then we can say that we can actually represent current and voltage as rotating phase vectors. That is, if let's say this is the current that is passing through a circuit, afterwards normally we used to represent graphs like this, right? Like a sinusoidal wave. This will be, let's say, current or voltage. Okay, this is V0, that is the maximum displacement here. So this is the graph that we are used to seeing. This is a sinusoidal wave graph. Now instead of doing this, we are actually going to represent the graph as a rotating vector graph or simply a phasor diagram. So we can take this particular graph and say that if voltage moved a certain step, that is, if voltage here, let's say at pi by 2 is indicated like this, or let's say voltage after, let's say one complete cycle is represented like this, like a wave, we can actually use a rotating phasor diagram to represent the same graph in a different way. That is, here the graph will rotate according to a particular angle. If this is pi by 2 or just simply 90 degrees, we can say that then this particular graph will rotate this much, that is 90 degrees, or let's say 30 degrees. Okay, then this will rotate this much, 30 degrees, or simply I can say that this line will indicate that particular quantity which is alternating. Let's say here it is V0, so I am going to take voltage itself there. So I am going to say this is voltage V, and then this particular angle between this axis and this rotating vector is known as the phase angle between them. So that is the gist behind this particular rotating vector diagram. So I am going to explain this particular vector diagram and how you can explain the various quantities that is lying inside this particular phasor diagram. So let's get right into it. So here we have an example in explaining this particular phasor diagram. So I told you phasor diagram is nothing but a rotating vector which represents the current and voltage using this particular setup. So here there is an arrow mark pointing outwards. So this particular arrow has a speciality, that is, the length of this particular arrow will give you the magnitude value of current and voltage. You can see here the current arrow is slightly smaller than the voltage arrow, which means that the magnitude value of voltage is slightly higher when compared to the current value, which means, so the magnitude value of this particular vector, that is current or voltage, is given by the length of that particular vector. If the vector is more lengthier, then we can say that the magnitude value of that particular vector is even more. So this indicates the magnitude value. The length indicates the magnitude value, and then there is an angle in between them. There is an angle in between I0 and this particular axis. That particular angle is known as phase angle. So, that particular angle is known as phase angle. So, the angle between the vector and the axis is known as phase angle, and we measure it in the anti-clockwise direction. So, we measure it in the anti-clockwise direction or simply towards the left. So, here the angle between current I0 and this particular x-axis is 5 degrees, which means, so the phase angle for current in this particular diagram is 5, and the phase angle for voltage is not omega t, but instead phi plus omega t. We have to measure the angle from this axis towards the particular vector. So that particular angle is phi plus omega t. So initially I told you that the length of this particular vector, that is the length of this particular vector, will give you the peak value. Peak value of current or voltage is given by the length of the vector. And now I told you about the phase angle between them. Now the third thing you have to primarily remember is that if I take the projection of this particular arrow onto the y-axis, you know that this particular vector can be resolved into x components and y components. It is known as also taking the projections of that particular arrow. You have learned it in your first PUC. So again, if I take the y-axis projection or the projection onto the y-axis, that is, if I take the y-axis projection, that is the vector projection of this particular vector, in here it is current. So if I take the projection onto the y-axis, I will get the instantaneous value of current in that particular point. So I will get the instantaneous value of current, and if I do it for voltage, I will get the instantaneous value of voltage. So I will get I and V. Remember, I0 is the peak value, and that is given by, or the peak value is given by the length of this particular vector. And here the projection onto the y-axis will give you the instantaneous value of current and voltage. The angle between the vector is known as phase angle. So between the axis where we start to measure the angle and the vector itself will give you the phase angle, and this particular angle, that is the angle between voltage and current. Now voltage and current are differing by an angle of omega t. That particular angle is known as phase difference. So current and voltage are now at a phase difference of omega t, or in other words, I can say that voltage is leading current by omega t, or I can say current is lagging behind voltage by omega t. So that is how we can actually use a phasor diagram to obtain this many data from this particular figure. So I can say what is the magnitude value of current, that is the peak value of current, what is the peak value of voltage, what phase the current and voltage are in, what is the phase difference between current and voltage, what is the instantaneous value of current and voltage. All this data can be obtained from a phasor diagram, and phasor diagram is nothing but a rotating vector. That is, the vectors are being represented as this alternating current and voltage are being represented as rotating vectors. That is known as phasor diagram. So since we got the question out of hand, that is what a phasor diagram is, we are going to dive into the deeper topics, that is applicational levels. When or what happens when current actually passes through, that is, so we are going to show what happens when current is being passed through a purely resistive circuit, which means there is only a resistor here, and a purely inductive circuit, that is only an inductor is going to be there, or finally a purely capacitive circuit, that is only a capacitor is going to be there. What happens when current is being passed through all three of these components? Will it be same? Will it be different? Will there be any clash? And finally we will see what happens when current is being passed through all of these together. That is, there will be a capacitor, there will be an inductor, and there will be a resistor. So all of these will be connected in series and AC current will be passing through them. Then what will happen? Will the combined effect be any different or similar to any of these equations? That is what we are going to see. So first, for that, we are going to pass AC current through a purely resistive circuit. So from Ohm's law, we actually know that V by I is equal to R, or simply V is equal to IR. Now Ohm's law is being applied to AC circuits and DC circuits. That's not a problem. The only difference is that instead of taking the average values, we are going to take the instantaneous values or simply the peak values. That is, instead of V and I, we are going to take V naught and I naught. I naught sin omega t and V naught sin omega t. So here again, the voltage can be represented as V naught sin omega t and I can be represented as I naught sin omega t. So now actually applying Ohm's law, we can actually find what is the current flowing through this particular circuit. So we can say that from this particular equation, we can say that I is equal to V by R, or simply applying these values, or simply by taking V naught and I naught, we can simply write I is equal to V naught divided by R, or I naught is equal to V naught divided by R. That is, I naught is equal to V naught divided by R. It's a simple derivation, only 2 steps are there. But what does this actually mean? It means that in a purely resistive circuit, current is directly proportional to voltage. That is what this equation means. That is what is the definition of Ohm's law itself means. The significance here is that current and voltage are actually in phase with each other, which means that if I draw a graph containing current and voltage, then I can actually say that if this is the graph for current, let's say this is I naught, then if I draw in the same graph, if I draw the voltage values, or if I trace out the voltage values, it will be like this. That is, current and voltage are actually in phase. The value of voltage may be slightly more, but actually current and voltage are in phase with each other. They are both moving together in this particular circuit. So if voltage is going through here, current is going along with that. There is no lag. There is no current going faster or voltage being followed. Both of them are in phase with each other. If this thing happens, then we can say both of them are in phase with each other. You don't believe me? You feel confused? Don't worry. That is why we have the phasor diagram. So the only thing you need to understand is that in a purely resistive circuit, that is, if there is an AC power source and that is being connected to a resistor, okay, a resistor of value R and AC source of voltage V, then the current flowing through that particular circuit I will be same phase with, that is, the current and voltage will be in the same phase in that particular circuit, and that is being represented as these 2 graphs. That is, both voltage and current are in phase with each other. So when current and voltage are traveling together, then we can say both of them are in phase with each other. If current is coming behind voltage, we can say voltage is leading, and if voltage is behind current, then we can say voltage is lagging behind current. So in this particular circuit, there is no other problem here because voltage and current are in phase with each other. And using a rotating diagram or simply a phasor diagram, we can say that both of them are in phase with each other because the angle between them, the phase angle between them is omega t, and the phase difference between them is actually 0 degrees because both of them are in phase with each other. The only difference is that their instantaneous values or simply their peak values are different. Other than that, both of them are in phase with each other. This is about a purely resistive circuit. Now we are going to change this resistor and put a capacitor, an inductor there. So again, same principle. There is a capacitor here instead of a resistor. The capacitance of that capacitor is C, and there is an AC power source having voltage V, and we are going to find out what is the current that is flowing through this particular purely capacitive circuit. So here current is passing through here, that is I. We are going to find that. The only thing we do know is that V is equal to V naught sine omega t. So that is the wave equation indicating voltage in an AC circuit. So we have that particular equation, and we also know that current is nothing but the flow of charges, that is dq by dt is equal to I. And we know that there is a capacitor connected to this particular circuit, and we know that current is nothing but the flow of charges, and we have an equation for the capacitance, that is C is equal to Q by V. C is equal to Q by V, or CV is equal to Q. So we can write CV is equal to Q. We have already learned this in the previous chapters that capacitance and charge is related through voltage times capacitance is equal to the charge. So we can say that, so if I take the derivative on both sides, then I'll get dCV divided by dt is equal to dq divided by dt. So we all know that dq by dt is nothing but I. And we also know that C is a constant, which means C will come right outside. So we can write C dV by dt is equal to dq by dt is nothing but I, which is the current flowing through that particular circuit, And now we also know that it is not just V, because V is equal to V naught sine omega t. So I can write it is C into, that is the left hand, I can write it is C into d V naught sine omega t divided by dt. So we can write that is equal to I. So again, V naught, the peak value is again a constant, because the peak value won't be changing. That is, if I draw a graph, the peak value, the maximum amplitude value is not going to change. So I can take V naught also outside. Then I can write CV naught d by dt of sine omega t is equal to I. Now, if we integrate sine, we know that we get cos. Now we have to apply chain rule here, because it is not sine theta but rather sine omega t. We know that if we integrate or differentiate sine, we get cos. So here d by dt of sine theta will be cos theta. Here it is d by dt of sine omega t, which means we have to get cos omega t into omega. So we can write CV naught cos omega t into omega. Applying chain rule, we will get this particular expression, or simply CV naught omega cos omega t is equal to I. So this is the expression, but it is not looking very nice. So what I'm going to do is that I'm going to take this particular quantity all together, that is CV naught omega all together, and I'm saying that, okay, this will be equal to I naught. So I'm saying CV naught omega is equal to I naught. Now, instead of cos omega t, I'm going to write it in terms of sine, because we are representing all these graphs in terms of sine omega t. The phasor graphs, the phasor diagrams, the normal graphs we saw, everything was represented as a sinusoidal wave graph. So instead of cos omega t, I'm going to apply the identity that I know cos omega t is actually equal to sine omega t plus pi by 2. That is a trigonometric identity. I'm going to apply that identity here. So I can write I naught sine omega t plus pi by 2 is equal to I. So current is actually equal to peak value of current. This is the current wave function. So I plus pi by 2, or simply I can say that current is actually leading voltage by pi by 2. So the physical significance of this particular equation is that current is leading by pi by 2, or simply we can say that using a normal graph which we are all used to, I can say that okay, current is 90 degrees forward, or we can say that pi by 2 times forward this particular voltage in this graph. It is a bit messy to understand from this particular graph. That is why we have to implement the phasor diagrams. Now we can actually say that voltage is lagging behind current. That is, we are measuring the angle from left, that is towards the left, which means voltage is only here while current is already here, which means current is actually leading by 90 degrees with voltage, or we can say that voltage is lagging behind current by 90 degrees, and the phase angle is omega t, and the phase angle between current and this particular axis is omega t plus 90, or simply omega t plus pi by 2. That is written here. Current is leading by pi by 2. The phase angle of this particular current or this particular vector is sine omega t plus pi by 2, or simply omega t plus pi by 2, because this graph is being represented as this particular rotating diagram or rotating vector diagram. Then we can say that this sinusoidal wave is represented like this, and the angle in between voltage and current is 90 degrees, which means the angle between voltage and this particular axis is omega t, which means the angle between current and this particular axis is omega t plus 90 degrees. That is being represented here, I naught sine omega t plus pi by 2. So current is leading voltage by pi by 2. That is what this expression actually means. So for a purely capacitive circuit, when current is passing through that, AC current is passing through that, current will be flowing much faster or leading by 90 degrees. So you only need a simple thing. We know that voltage can be represented as V naught sine omega t. We know the equation for capacitance, which is Q by V. So we rearrange that particular equation. We get CV is equal to Q. From that, we take the derivative on both sides. We get I is equal to C dV by dt. C is a constant. It comes right outside. Here it is not V. It is V naught sine omega t. So from that, we can write CV naught. Since these two quantities does not change, we can take it outside. And the only remaining quantities is sine omega t by dt. So again, differentiating sine, you will get cos, and applying chain rule, we get cos omega t times omega, and taking all the constant terms together, that is C, V naught and omega together, I am calling it as I naught, then I can say I naught cos omega t. But instead of writing cos omega t, I have to use a sinusoidal wave function. So I am going to take the sine graph. So I can convert this cos omega t into sine using trigonometric identity. So I can write cos omega t is equal to sine omega t plus pi by 2, and simply voila, pops in this identity, that is I naught sine omega t plus pi by 2. So that is all about a purely capacitive circuit. And finally, we are going to see what happens when current is passed through a purely inductive circuit. Instead of a capacitor, we are going to pass an inductor there. So what will happen there? So we have a circuit that is AC power source connected to an inductor, and current is being passed through that. So we are going to find out what is the current that is flowing through this particular circuit. That is a purely inductive circuit. So again, we'll start with the equation we all know, that is V is equal to V naught sine omega t. Now here it is an inductor having inductance L. What is an inductor? What is inductance? Everything has been discussed in the previous classes. And we also know one particular equation that is relating EMF. EMF is nothing but voltage. So we have one equation that is relating EMF and inductance together. We know that E is equal to L di by dt. So we have that particular equation. We are going to apply that particular equation here also. But first, we are going to write V is equal to V naught sine omega t. That is the voltage in this particular circuit. And then we know what is the equation for inductance, and we are going to write it down. That is E is equal to L di divided by dt. This E specifically points out to voltage. That is, electromotive force is nothing but voltage. So in this particular case, we can actually say that E is equal to V, which means V is equal to L di divided by dt. Making a slight rearrangement, I can write V divided by L, and taking this dt here, V divided by L into dt is equal to di. Now again, what are we trying to find? We are trying to find what is the current that is flowing through this particular inductor. So for that, the only thing we can do is integrate. If I integrate on the right hand side, I will get capital I, the current. And on the left hand side, if I make one small substitution, that is V is equal to V naught sine omega t, I can write this as integral V naught sine omega t divided by L is equal to I. Now, again, L is a constant, V naught is a constant, comes right outside. So I can write V naught divided by L integral sine omega t dt is equal to I. Now, what is integral sine omega t dt? So we do know that integral sine theta is nothing but negative cos theta. So I can write V naught divided by L into negative cos, here it is not theta but rather omega t, which means again we have to apply the chain rule, which means minus cos omega t divided by omega. If it was differentiation, we can multiply, but here it is integration, so we have to divide by omega. So omega is equal to I. So we again have one equation, that is V naught by L omega into minus cos omega t is equal to I. Again, the only problem here is that it is expressed in terms of cos omega t. We have to express it in terms of sin omega t. Then only we can draw the graph and phasor diagram. Even if you don't want to draw the phasor diagram, I have to make you draw the phasor diagram. So minus cos omega t, just by using a trigonometric identity, we can write it as a sine component. So for that, I'm going to apply the trigonometric identity, that is minus cos omega t is actually equal to sine omega t minus pi by 2. Minus cos omega t is equal to sine omega t minus pi by 2. So I can actually write V naught by L omega into sine omega t minus pi by 2 is equal to I. So what does this equation mean? Later we saw, just before we saw that, in terms of purely capacitive circuit, it was plus pi by 2, and we just figured out that current was actually leading by 90 degrees. Here it is minus pi by 2, which automatically means that current is now lagging behind 90 degrees. Now voltage is leading by 90 degrees. That's the only difference. Otherwise everything is same. That is, if we draw the phasor diagram and the graphs for this particular equation, we will get, that is, if we draw the graph for a purely inductive circuit, we will find out that, so if we draw a graph to find out this particular or express this particular equation, we can see that current is now lagging behind voltage. That is, current is lagging behind voltage by 90 degrees. So in the phasor diagram, it is clearly expressed voltage is now leading by 90 degrees, while let's say voltage is here expressed by a phase angle of omega t, then I can say that current is now lagging behind voltage by pi by 2 or simply 90 degrees. So this is the phasor diagram indicating that. This is the normal diagram which you are used to representing current and voltage as AC power sources, and this particular equation conveys us that the phase angle or the phase angle difference is pi by 2 in between these two. Generally, we can say that if you have any doubts regarding phase angle and phase difference, we can say that this particular angle is the phase angle, and plus or minus whatever we write after that is the phase angle difference. Okay, so here this is the wave function sine, that is the sinusoidal wave, and then after that omega t is nothing but the phase angle which it makes, and after that plus or minus pi by 2, pi or 2 pi, whatever it is, let's call it phi. So that particular phi here, it is minus pi by 2, indicates the phase angle difference between these two vectors. So here it is 90 degree. So here automatically current is lagging behind voltage by 90 degrees. And in the previous case, current was leading to voltage by 90 degrees. That is the only thing. It's a fairly simple derivation. The only thing you have to understand is that minus cos omega t is equal to sine omega t minus pi by 2. That's the only thing. So, okay, since we saw what happens to current in all of these circuits, we have to also learn one small thing, that is the resistance offered in all of these circuits. That is, we have to find what is the capacitive resistance and the inductive resistance. We don't have to find out that for a purely resistive circuit because resistance itself is mentioned there and both current and voltage are in phase with each other. But here for a capacitive circuit, we know that current is leading by 90 degrees. So we have to express or find an expression for capacitive reactance, or simply the resistance offered in a capacitive circuit. So we know that this particular I naught, this is the equation for a purely capacitive circuit in terms of current. So we know that for a capacitive circuit, I naught is actually equal to C V naught omega, right? C V naught omega, or simply rearranging this particular equation, I can say I'll take this I naught here and C and omega to the left side. That is, I'm going to take these two quantities to the left hand and this quantity to here. So I'll get 1 by C omega is equal to V naught divided by I naught. Right. Why I did this is because we all know that the famous Ohm's law equation, that is V by I is equal to R, or V is equal to IR. So here in this particular expression, we know that R is resistance. Just like that, here 1 by C omega is now actually being equated to resistance. So we can actually say that 1 by C omega is the capacitive reactance of this particular circuit. It's a fancy way of saying it is the resistance offered here. So here I can say 1 by C omega is equal to capacitive reactance, or simply it is indicated by not R but rather chi C. Chi is the reactance or simply resistance offered in this capacitive circuit, and this is the expression for that particular capacitive reactance, that is 1 by C omega is equal to chi C. Similarly, we have to also find what is the capacitive reactance of a purely inductive circuit, or simply what is the capacitive reactance for an inductor. So again, we know that current is expressed using this particular equation, that is I is equal to I naught sine omega t minus pi by 2. And we, from that particular expression, we know that I naught can be expressed as V naught by L omega, that is V naught by L omega is equal to I naught. So from this, again we are going to apply nothing but Ohm's law. So we know that V naught by I naught is nothing but reactance or simply resistance of that particular circuit. So here it is purely inductive reactance, or simply the resistance offered by the inductor. So I can simply say V naught divided by I naught is equal to L omega, that is the reactance offered, and that can be written as chi L. So this is known as inductive reactance. There it was known as capacitive reactance. Here it is known as inductive reactance. Now I get it. You have a confusion. Why are we learning this resistances in AC circuit? Why is it being given chi C and chi L? What is the physical significance? Even if you are not thinking about it, it is my duty to explain that. So I'll tell you what this particular equation actually means. So you can clearly see here that L omega is equal to chi L. I'll do one thing. I'll write down the capacitive reactance and inductive reactance, and I'll tell you what is actually going on side by side. We can do a comparative study. So, okay, this is just a comparative study between capacitive reactance and inductive reactance. So, we can say that chi L, that is inductive reactance, is equal to L omega, while capacitive reactance is equal to 1 by C omega. So, again, it is the effective opposition, generally the resistance. So, effective opposition offered in a purely inductive circuit, that is chi L, and if it is offered in a capacitive circuit, it will be chi C, 1 by C omega. That is the only difference. Now, if I draw the graphs between these two resistances versus frequencies of this particular purely inductive and purely capacitive circuits, then I'll get shockingly different values. The only difference is that one is 1 by C omega and the other one is L omega. So again, to get frequency, you know the simple thing. L omega can also be written as L into 2 pi mu. That is omega, and omega is angular frequency and mu is linear frequency. Their relation is 2 pi mu. So again, here I can write it as 2 pi mu. Again, you know that C, 2 pi, both of them are constants. Here also L and 2 pi, both of them are constants, which means I can derive a relation that is chi L is directly proportional to mu here, and here chi C is inversely proportional to mu, which means if I draw a graph between chi L and mu, that is frequency and resistance, I will get a straight line like this, which means in an inductive circuit, the more current I allow to pass through, the more resistance it will create. So if I allow more AC current to pass through an inductive circuit, more resistance will be offered, more opposition will be offered. Now here, it is inversely proportional. So in a capacitive circuit, capacitor stores charge, which means that in a capacitive circuit, so if I allow more current to pass through, or simply if I increase the frequency, then a funny thing happens to the resistance, because the resistance value actually decreases. So it will be a slightly curved graph like this because it's an inverse graph. So according to inverse rule, we can get a curved shape like this for the graph. So that is the difference between inductive reactance and capacitive reactance. So what it actually physically means is one small thing is there. I'll discuss that also with you. So the physical significance is that one of these allows AC current to pass through and blocks DC current. The other one allows DC and blocks AC current. So which one do you think allows AC current to pass through or allows DC current to pass through? Let's go with DC. So which of these circuits do you think allows DC current to pass through? Which do you think? Don't know? It's very simple. Look at the frequency. For a DC current, I told you, if you are taking DC, there is no phase, there is no difference, there is no frequency. Because frequency means number of cycles that is repeating. There is no cycle, it's unidirectional. Which means for AC current, if I draw a graph, AC current will go like this with a lot of frequencies. But for DC current, there is no frequency practically. Which means that for AC current, as the frequency increases, this chi L, ideally I can see that if I have infinite frequencies, then I'll get resistance also as infinite, which means AC current is blocked by this particular circuit. So I can see that inductive circuits or purely inductive circuits will only allow AC current to pass through. So I can write here that allows allows only DC current to pass through. Allows DC current only. So it does not allow AC current. Do not allow AC to pass through. It does not allow AC to pass through, and it only allows DC current to pass through. Again, right opposite will be happening here, which means it allows AC and blocks DC. Again, it is very simple because 1 by 0 will be 0. That is, here it only allows DC because chi L is equal to 2 pi mu, right? Here it only allows DC means chi L is equal to 2 pi mu, which simply means that here mu is 0. There is no frequency, there is no change. So if mu is 0, this resistance part, this opposition is actually equal to 0. There is no resistance. Hence, current can easily pass through. DC current can easily pass through. If AC current is allowed, then as frequency increases, opposition also increases, which in definition means that AC is not allowed to pass through. Then here for a capacitive circuit, it's very easy again. If I take the same equation, that is chi C is equal to 1 by C 2 pi mu. Again, here the value of mu is 0 for DC, which means 1 by 0. 1 by 0 is actually infinity, or undefined actually, but let's say infinity. So which means it offers infinite resistance. So it offers infinite resistance to DC current. But what happens to AC current? AC current, which means mu will have a value, a high value, which means as this value increases, this decreases, which means the opposition or resistance offered will actually decrease as we use AC current. That is why for a capacitor we can actually use AC current, but for an inductor we cannot use AC current. That is the only difference. If you want to imagine it in your head, a capacitor will charge and discharge constantly with AC current, but for DC current it can hold that particular charge. So that is the difference. You can find many animational videos online, that is especially for engineering's point of view. You can find a lot of videos for that, but this is the relation between these two. I hope there is no confusion in that. So we studied about a purely inductive, purely capacitive and purely resistive circuits, and now in the next class we will be dealing with a purely, not purely, but actually we will be dealing with a series LCR circuit. Series LCR, that is inductive, capacitive and resistive. So all these will be put together and we will see what happens when current is passing through those circuits. So I'll see you all then. Thank you.